Okay, yeah. Thank you for having me in your group meeting today. Yeah, I can introduce myself again. I'm a final year PhD student at the Max Planck Institute of Astrophysics in Garching, working with Eiichiro Komatsu. And today I would like to share with you the results of our projects on early dark energy using the profile likelihood. But before I talk about the profile likelihood, I give an introduction about the idea behind early dark energy. So I try to be a little bit more quick because there are so many experts in the audience here. And then I will discuss whether early dark energy solves the Hubble tension. As you might know, or as you will see, there's some disagreement about this question in the literature. And then I will discuss our constraints with the profile likelihood, which we were motivated by understanding this disagreement in the literature. And please, if you have questions or comments, you can interrupt me anytime. So as you all know, there's a discrepancy in different measurements of the expansion rate, the Hubble constant. And taking into account the most recent Schulz result, one ends up with a 5 sigma tension with Planck. But the interesting part about the Hubble tension is, of course, that it's not only a tension between two experiments, but between two classes of experiments. On the one hand side, the direct measurements that do not or only weakly depend on a cosmological model, and the indirect measurements which need to assume a cosmological model, usually flat lambda CDM. And now the big question is whether this tension is caused by systematics or new physics. And in this talk, we simply forget about the systematics and ask, what if this tension is caused by new physics? There are many, many ideas how one could solve the Hubble tension, but one can group them into classes. And in order to understand these two classes, it is instructive to look at this quantity, theta s, the angular size of the sound horizon, which is very precisely measured by Planck. And therefore, we can assume it to be fixed by observation, essentially, because it's given by the frequency of the oscillations in the power spectrum. So the early time solutions of the Hubble tension, they modify the physical size of the sound horizon, whereas the late time solutions modify the angular diameter distance to last scattering. And there has been this very nice paper last year that was called the H-Node Olympics. And essentially, all the models that made it to the finals were early time solutions. So it seems like the early time solutions work better. And the reason being that the tomographic data that we have at late times clearly disfavored these late time solutions. Yeah. And in this talk, we're focusing on early dark energy, which performed rather well in this comparison. And so what is the idea behind early dark energy? The idea is to introduce an additional component at early times that boosts the expansion rate at early times, such that this integral here is suppressed. The integral goes from the redshift of recombination until the Big Bang. Now, if this integral here is suppressed, but theta s is essentially fixed by observation, if the physical size of the sound horizon goes down, also dA has to go down. And if one looks at this integral, which goes from today to the redshift of recombination, and one assumes that the matter content is approximately fixed, the easiest way to achieve this is essentially by increasing H0. And this is what is needed to solve the Hubble tension. And more precisely, early dark energy needs to start becoming relevant just before recombination, because this is where this integral is most sensitive to. It behaves like dark energy at early times in order to boost the expansion rate sufficiently. And its energy density needs to dilute faster than matter after the redshift of recombination in order not to impact the CMB measurement too much and late time physics too much. So how could one realize such a rapid energy injection? Here we consider the so-called canonical EDE model, which is a scalar field with this 1 minus cosine potential to the power of n. So this model has 4 free parameters: the mass, the decay constant, the initial value, and this index n. But we will fix this index n to 3, which is very common in the EDE literature, because it was shown that n of 3 fulfills the EDE requirements. In general, n larger equals 3 fulfills the EDE requirements, but n of 1 or n of 2 leads to a field that doesn't decay quickly enough. So this field is inspired by the axion, For an axion-like potential, one would expect n of 1. So it's an field inspired by the axion with extremely small mass. And if we have a look at the dynamics of the field, in the beginning, Hubble friction dominates. So the field is essentially frozen at the initial position and behaves like dark energy, very similar to the inflaton field. But of course, the EDE is much later than the inflaton field at much later times. And that at some critical redshift, the mass term dominates, the field starts rolling down the potential and oscillating around the minimum. And in this phase, the field decays faster than matter. So the equation of state looks like this. So W is -1 for redshifts earlier than the critical redshifts. And W is for n equals 3 is 1/2 for redshifts later than the critical redshift. And this is what the time evolution of the field looks like. So at early times, there's this rapid growth. Then the field starts oscillating and starts to decay. And at the redshift of recombination of around 1,000, the field is already almost decayed. So from the particle physics parameters, one can calculate the more phenomenological parameters, the fraction of early dark energy, so the maximum fraction of early dark energy at the critical redshift CC, and the initial value of this scalar field theta I. So introducing this EDE field means introducing 3 additional parameters compared to lambda CDM. And usually to solve the Hubble tension, one aims at about 10% of early dark energy. So how does early dark energy fare when compared to data? So can early dark energy solve the Hubble tension and simultaneously fit all available cosmological data sets? And if one looks at this dataset combination here, which consists of the Planck CMB, the galaxy clustering data from 6, the FGS and BOSS, and the Cepheid calibrated type 1a supernovae from Pantheon and SHOES, one finds that yes, EDE can solve the Hubble tension. And if one runs a full MCMC on these data sets, one finds that the data prefers about 11% of early dark energy and an H0 of about 71.5. So reducing the tension with SHOES, which is the gray line here. And the EDE cosmology is the purple line. So actually the mean shifts to higher values and also the error bar increases. However, one cannot simply introduce early dark energy and only H0 increases, but also other parameters shift. And this is because early dark energy acts as a dark energy component at early times. So it suppresses the growth of perturbations at early times. And in order to compensate this suppressed growth, one needs more cold dark matter and a higher spectral index. And this means at late times, the amplitude of matter clustering, sigma 8, increases, worsening the already existing so-called sigma 8 discrepancy. One can also see this if one plots the Metapower spectrum. In EDE cosmologies, the red line, there's an enhanced clustering at small scales. Now, in this study, they discarded the SHOES measurement and they included weak lensing experiments, which are particularly sensitive to sigma 8. So with that, one can probe the compatibility essentially of EDE with the sigma 8 tension. And the first thing they find is that when they run a full MCMC only on the Planck dataset, they find that the Planck dataset disfavors EDE, so the red line here. And if they include the weak lensing data without SHOES, the teal line here, they find a very tight upper limit on the fraction of early dark energy of FED smaller than 6%, and H0, which is compatible with SHOES. And only if one includes SHOES in the data sets, so this is SHOES without weak lensing, then SHOES with weak lensing, there's a preference for the EDE model. So I think the main conclusion here is if there's no SHOES in the data set, there's no preference for early dark energy. Also, one can, as a different observable of the large-scale structure, one can include the full shape analysis based on the EFT of large-scale structure, so the full shape analysis of BOSS galaxy clustering, and one finds a similarly tight upper limit on the fraction of early dark energy. And the conclusion is that early dark energy cannot restore cosmological concordance because Planck alone doesn't prefer early dark energy, and Planck with large scale structure gives these very tight upper limits. However, several authors have pointed out that these constraints could be biased by prior volume effects. So what are prior volume effects, also known as projection effects or marginalization effects? They appear if the MCMC posterior is strongly influenced by the prior volume. And reasons for this can be that the model has too many parameters, or equivalently the data is not constraining enough for all those parameters, or also if the posterior is very non-Gaussian. And if one looks at the 2D posterior of the critical redshift versus the initial value of the EDE field, one finds that the data does not constrain those two parameters very well. And also that the posterior is very non-Gaussian. Then also, the parameter structure of the model can generate large volume differences. And this happens in the EDE field when the fraction of early dark energy goes to 0, so no early dark energy. Then the two parameters that describe the EDE model further, the critical redshift and the initial value of the scalar field, they are completely unconstrained if there's no early dark energy. And one recovers the lambda CDM limit. However, one recovers the lambda CDM limit with essentially two extra dimensions. So if an MCMC chain explores the parameter space around FAD of 0, essentially a huge parameter space opens, lambda CDM with two extra dimensions, and the chain can spend a long time exploring those two extra dimensions because they have a large volume. And this can lead to a bias in the marginalized posterior. So there's no problem in the full n-dimensional posterior. It's only if one integrates out those two unconstrained parameters, which can lead to a bias in the FAD parameter. So a bias towards FAD of 0. And to illustrate these prior volume effects, I picked one example from the literature in the context of lambda CDM, not EDE. So this is taken from a DS collaboration DS3 analysis paper, where they tested their analysis pipeline on simulated 3x2 point data in the context of lambda CDM. And they tested two different analysis choices. One is that the omega nu, the energy density in neutrinos, is a free parameter and is marginalized over. And one is that omega nu is fixed. And they find that in the case where omega nu is free, they find a small bias of the omega m S8 posterior with respect to the true underlying cosmology. And the interpretation is that omega nu is poorly constrained by the 3x2 analysis, and that the shift in the 2D contours indicates a projection effect from marginalizing over an under-constrained parameter that is correlated with the parameters shown. So although we're not even plotting omega nu, the fact that omega nu is not constrained and is integrated out can lead to this small bias. So here the conclusion would be, since omega nu is not constrained anyway by the data, it makes sense to fix it to m nu to 0.06 in the baseline analysis. Now coming back to early dark energy, these two groups, they had a similar idea in the context of early dark energy. If the data cannot constrain all parameters of the early dark energy model, why not simply fix two parameters of the model? And they fixed it to the best fit obtained to Planck only data. And this is what they named the one-parameter EDE model. And in the one-parameter model, they only vary FEDE. And they find that for the same data set that before ruled out early dark energy, so Planck plus Boss full shape analysis plus the Pantheon data set, they found that these data sets prefer about 7% of early dark energy, which can essentially resolve the Hubble tension. So although they used the same data set, they came to completely different conclusions than the studies before. And they suspect that the reason behind this difference is prior volume effects. However, simply fixing two parameters of the model is not a full Bayesian analysis, because for us, it was, for example, not clear how the inferred amount of early dark energy depends on the choice of these two parameters. In the case of the one-parameter model, they fixed it to the best fit to Planck. But I think this is also tricky because one uses the same data set to fix those two parameters, and then one uses it to analyze the reduced model. So fixing two parameters is not a full Bayesian analysis. So our idea was to use the profile likelihood because it is not subject to prior volume effects. But before I talk about the profile likelihood, I would still want to mention the recent results from the Atacama Cosmology Telescope, because there were two independent analyses which found that actually the Atacama Cosmology Telescope prefers the EDE model over lambda CDM by 2 to 3 sigma. And that essentially with the ACT dataset, EDE presents a resolution to the Hubble tension. So if you look at this 1D posterior, the red is Planck data only, and the solid is the lambda CDM model, the dashed is the EDE model. And for Planck alone, introducing EDE cannot shift H0 to much higher values. But for the ACT dataset, which is the blue one, introducing early dark energy leads essentially to complete overlap with the shoes constraint. And the baseline dataset is the yellow, which also includes lensing and BAO. And for the baseline dataset, they find that the data prefers an H0 of 71 and FED of 9%. And they try to understand where this preference for early dark energy in this dataset comes from. And they found that it's essentially driven by seven bins of the TE and EE polarization power spectra. But it's not clear whether these 7 bins are driven by systematics or by new physics. So it might be interesting to wait for the new ACT data release. So to summarize the status of early dark energy at the moment, so the question is early dark energy ruled out or not? If one includes shoes in any type of analysis with any other kind of data set, one finds that early dark energy solves the tension. However, if one looks at CMB alone or CMB combined with galaxy clustering or combined with weak lensing, one finds in a full MCMC that early dark energy is ruled out. However, for the same data sets, using the reduced EDE model, one finds that ED solves the tension. And then additionally, the ACT data says ED is preferred by the data and solves the tension. And we were in particular interested to understand what is going on here and whether prior volume effects are the reason behind this. So let's check for these prior volume effects using the profile likelihood. So what is the profile likelihood? The profile likelihood is a method from frequentist statistics, which is used to construct confidence intervals. And to construct a profile likelihood, one fixes the parameter of interest, let's call it y here, to different values, and one minimizes the chi-squared or maximizes the likelihood with respect to all other parameters of the model. So for example, for early dark energy, if we're interested in FED here, we would fix FED to different bins and minimize all with respect to all lambda CDM parameters and the 2 remaining EDE parameters and all nuisance parameters. And this, if the parameter is Gaussian distributed, this gives a parabola in delta chi-squared. And now, according to the Neyman construction, one obtains the 1 sigma confidence interval by finding the intersection of the profile likelihood with delta chi-square of 1. So this here is the 1 sigma confidence interval. And one finds a 2 sigma confidence interval at delta chi-square of 3.84 and so on. And there's one small complication. So add a physical boundary. That means add a parameter border that is where the parameter would become unphysical. One needs to use the so-called Feldman-Cousins prescription, which is a generalization of the Neyman construction. And we will use the Feldman-Cousins prescription later, but it's a little bit technical, so I'll move the slides into the backup. But if somebody's interested in this prescription, I can also explain it later. So why would it be interesting to look at the profile likelihood if one already ran an MCMC? And for that, I have a small comparison of the 2 methods. So the MCMC constraints are based on the Bayes theorem, which says that the posterior is proportional to the likelihood times the prior, where the prior is given, for example, by theory or by previous experiments. And because the likelihood is weighted by the prior volume, the posterior has the property that it identifies bulk volumes, so large volumes that fit the data well. On the other hand, the profile likelihood is based on a much simpler quantity only on the likelihood. So there's no posterior, no prior. And both methods have different problems. Like we already said that the posterior can be subject to prior volume effects, but the profile likelihood can have the exact opposite problem, because the profile likelihood is not weighted by any kind of volume. It can prefer a cosmology with very small parameter volume, so with very fine-tuned parameter space. And like one could solve these two problems. For example, the prior volume effects one could solve by using more or better data, or a model with less free parameters. And to solve the fine-tuning problem, of course, one can also use more data, or one could construct a physically well-motivated model. Since for the EDE model, there's none of these solutions are available, although people are also working on physically better motivated models. As long as those solutions are not available, I think it makes sense to look at both methods, and in particular use the profile likelihood in order to verify the results from the MCMC. And one example where the profile likelihood was used to verify the MCMC results is in this Planck collaboration 2013 paper, where they ran a profile likelihood analysis for all the lambda CDM parameter in order to verify the MCMC result. And for every lambda CDM parameter, they found perfectly consistent results between MCMC and profile likelihood. And they found one interesting observation. So it doesn't change the numerics, but it helps in the understanding where the constraints are coming from. And the interesting observation is in the sum of neutrino masses, mu. And they find that if they look at Planck data without lensing, they find this solid line. But for Planck data with lensing, they find this dashed line. So this might seem a little bit counterintuitive on first thought, because adding more data here degrades the constraining power. However, this makes sense when one looks at the profile likelihood, because for the Planck data without lensing, the best fit is actually far in the negative. But for including lensing, the best fit shifts to 0. The constraining power increases because the parabola gets narrow. However, if one cuts the posterior here at mu of 0, this leads to this counterintuitive behavior. But for the new Planck data release, this also disappeared. So for the new Planck data release, also without lensing, I think has a best fit of 0. So this was only in the old Planck data release. So now coming back to early dark energy, we now want to compute a profile likelihood in the fraction of early dark energy and in H0. And for that, the first step is to maximize the likelihood for FEDE fixed or H0 fixed respectively to different values. And the second step is to fit a parabola to the profile likelihood from step 1. And then we construct the confidence interval using the Feldman-Cousins prescription. So for the first step, as I already mentioned before the talk, we use the simulated annealing-like technique, which was already used in the H0 Olympics paper. And for that, we run several small MCMC chains with Monty Python essentially, with successively decreasing step size and successively enhanced sensitivity to the likelihood difference in the Metropolis-Hastings algorithm. So we also modify the Metropolis-Hastings algorithm a little bit exactly like in the H0 Olympics paper, such that the acceptance probability is not only given by the likelihood difference, but it can be tuned by this factor F, and this sets the temperature. And yeah, we tested this, for example, we compared this to Migrate and Bobby QA. And for Migrate and Bobby QA, we essentially found only noise instead of a profile likelihood, but this method really worked well for the EDE model. To model the galaxy power spectrum, we use this code called class PT EDE, which is a combined class PT and class EDE version. We use the following data sets. We use Planck 2018 with lensing, the BOSS DR12 full shape analysis based on the effective field theory of large-scale structure. Then we include the dark energy survey results as a Gaussian likelihood on S8. And we include the shoes result as a Gaussian likelihood on H0. And as I already mentioned, we use the full shape analysis of the power spectrum based on the effective field theory of large-scale structure. Even if you're not convinced about the EFT of LSS, our results do not depend on whether we use EFT of LSS or only Planck or Planck plus PO, so we checked that. But in our baseline result, we use the EFT of LSS. And I have one slide to explain the basic idea. So EFT of LSS is based on perturbation theory. So the galaxy power spectrum multipoles are given as a sum of the 3 power spectrum part plus a 1 loop power spectrum part, which is the perturbation theory up to 4th order in density contrast, and then plus a short noise term, and plus the counter terms. And where the counter terms are supposed to absorb the unknown small scale physics. So they are in particular supposed to absorb the fact that dark matter is not a perfect fluid, and the influence of the very small nonlinear scales on the mildly nonlinear scales and on the linear scales. And by using this EFT approach, we introduce 8 nuisance parameters, 4 galaxy bias parameters, 3 counter terms, and 1 short noise term. And one introduces those 8 nuisance parameters for each of the BOSS data sets. So we introduce 8 times 4 nuisance parameters, essentially. And one small note here. There was recently an update in the BOSS window function treatment, which was introduced here in this Beutler-McDonald paper. And in the following results, we also included this, we implemented this bug fix in our EFT of LSS likelihood. And now coming to our results. The first step that we did was we ran a full MCMC on our baseline data set, which is Planck plus BOSS full shape data. And we recover essentially the results that were found before, which is also important because the results from before, they didn't include this BOSS window function update yet, but it changes only a little bit for early dark energy. So the conclusion should still be the same. So we find also this tight upper limit on the fraction of early dark energy. And one can essentially see this prior volume effect here, because when early dark energy, the fraction of early dark energy goes to 0, the critical redshift and the initial value of the ED field are completely unconstrained. And now we construct profile likelihood for the same data set, which looks like that. And the 1 sigma confidence interval gives about 8 to 9% even of early dark energy. So although it's exactly the same data set, the MCMC gives this very tight upper limit, whereas the profile likelihood prefers actually about 9% of early dark energy. And we also constructed a profile likelihood in H0, which is this here. And we find H0 of about 70.6, which is consistent with shoes at 1.4 sigma. So shoes is here the gray area. And for comparison, the red area is the Planck H0 obtained within lambda CDM. However, we also find what previous analysis found. We find that within the EDE model, the S8 tension worsens slightly. So these here are the S8 best fits for lambda CDM. We find 0.8 to 8. This increases a little bit in the early dark energy model with 0.84 and worsens the tension with the DES measurement. Okay, so in order to probe this worsening of the S8 tension, we combine our baseline result with the dark energy survey result compressed in a Gaussian likelihood on S8. And we find, as expected, that the preference for early dark energy decreases to about 6%. And also H0 decreases slightly, but is still consistent with shoes at 1.6 sigma. So this is the blue dashed line here. So we find that including lensing reduces FED in H0 slightly, but that does not rule out early dark energy. So it seems like that the prior volume effect are the dominating effect that push the fraction of early dark energy to small values, and with that also H0 to smaller values. And it's not so much the physical effect of the increased clustering, which only gives a very small decrease in FED. So because our baseline result is consistent with the shoes measurement, it makes sense to combine our baseline data set with shoes and do a combined profile likelihood analysis. And we find a very large FED as expected, so about 13%, and a very large H0 of 72, which is consistent with shoes at smaller 1 sigma. So now we were also interested in how much from the constraining power comes actually from Planck alone without large-scale structure data. So we ran a profile likelihood with only Planck, and we find that the Planck-only constraint is actually very similar to the Planck plus Bose shape constraint. So we find FED of about 7% and an H0 of about 70. And this is in agreement with shoes at 1.7 sigma. So what we found interesting about this is earlier I mentioned this recent Atacama Cosmology Telescope result. And we find with the profile likelihood that the 1 sigma confidence interval actually perfectly overlaps with the ACT constraint coming from MCMC. So this might be also a coincidence, but we still found it curious. And so in principle, one could say one could explain the difference between ACT and Planck by prior volume effects in the MCMC. But I think this is a little bit early to say. And so in this plot, I show all the results together. So the upper 4 arrow bars are from the profile likelihood, whereas the lower one is from the MCMC. So we find that for all data set, the profile likelihood prefers a much higher amount of early dark energy and much higher H0. And this is a preference, or this is a evidence for prior volume effects in the MCMC. And we find that the H0 and the EDE model is within 1.7 sigma of the shoes measurement for all the data sets that we considered here. So also including galaxy clustering and weak lensing. So we find that EDE presents a viable solution to the Hubble tension. Because one more thing that we wanted to look at is which model is preferred from a model selection perspective. So is it early dark energy or lambda CDM? I mean, one measure one could use for model selection would be only the goodness of fit, so only the delta chi-square. But the problem is then, of course, that there would be no penalty for extra parameters, because of course, when we add 3 more parameters, it has to fit the data at least as well as lambda CDM, because EDA has the lambda CDM limit. So we wanted to look at this Akaike information criterion, which is defined as delta chi-square plus 2 times the number of extra parameters. And this penalizes the additional parameters in the extended model along the philosophy of Occam's razor. So we look at this Akaike information criterion for our 4 different dataset combinations. We compute the delta chi-square and the delta AIC. And essentially we find a mild preference for lambda CDM for all datasets that do not include shoes. And we find a clear preference for the dataset with shoes, which is kind of expected, because all of these datasets here don't include the Hubble tension, of course, so only the one with the Hubble tension gives a clear preference. But the fit, even when penalizing the additional parameters of the EDE model, is similarly good as lambda CDM. So EDE also presents a fairly good model to those datasets. And yeah, I have one short extra section if you're interested, because so far we only talked about the Hubble tension, and we saw that the Hubble, like FED or early dark energy, makes can solve the Hubble tension, but makes the S8 tension worse. And we looked at one idea how one could solve both tensions. I don't know if it's 2 slides. Should I still go through them, or?
I would be happy.
Please go ahead, yes.
Okay, yeah, it's not much. So the idea is very simple. As we know, the more early dark energy we have, the stronger the enhancement of the clustering in small scales. But we all know one candidate that suppresses clustering at small scales. So we thought maybe introducing a higher neutrino mass can compensate the increased clustering and essentially bring S8 back to the lambda CDM value. So could higher neutrino masses compensate the worsening of the S8 tension in EDE cosmologies? And so the short answer is it doesn't work very well, but we wanted to understand why. So what we did is we did a profile likelihood analysis in mu, so the sum of neutrino masses, with all the EDE parameters free. And we find that the best fit is at the lowest allowed neutrino mass at 0.06 electron volts. So the red is ruled out by neutrino oscillations. So there's no preference for larger neutrino mass in the EDE cosmologies. And as expected, we find a positive correlation between the sum of neutrino masses and the fraction of early dark energy. So the higher we fix mu, the more early dark energy is preferred by the data. So the degeneracy is there. However, to reduce the S8 tension only to the lambda CDM limit, so not even to solve the S8 tension, one needs a neutrino mass of 0.24 electron volt. Because of the degeneracy, we get a high H0, but the fit worsens by delta chi-square of 7.5. And then we looked where the most of the constraining power comes from, and it's the same as in lambda CDM, as at very high neutrino masses, we found that the constraining power comes from the BAO scale mainly. And yeah, so if the S8 tension persists, this is of course a problem for early dark energy, and one needs to introduce even more exotic physics probably. So it needs an independent late time solution. Okay, and this brings me now to my summary slide. So prior volume effects are important for beyond lambda CDM models that introduce many additional parameters compared to lambda CDM. We mainly looked at early dark energy, but we also looked at a certain decaying dark matter model, where we also find that prior volume effects are important. And we use the profile likelihood because it's not subject to the prior volume effect. And we find that early dark energy is a viable solution to the Hubble tension. And in particular, it's not ruled out by a large case structure. And so I think that frequent Bayesian methods are powerful complementary tools because both have different shortcomings, but using both helps to mitigate the shortcomings of both. So thank you for your attention.